Welcome to Rubber Duck Engineering. Tonight, we're going to play with LD preload, a loader environment variable to let you inject whatever. We'll get to it. Hi, Dr. Barth.
Hey, Eric, what are we going to LD preload?
We're going to LD preload our simple malloc that we've been writing these last couple weeks.
We're going to ship our simple malloc by jamming it into somebody else's program and hoping that it doesn't destroy the whole thing.
Orders of magnitude slower than the default malloc.
Or maybe make fireworks or like melt the computer. Like who knows what horrible thing will happen.
Well, hopefully the kernel is still intact and will protect the
it will protect the computer from catching on fire.
Yes.
This is true. At least it's supposed to.
Yeah, I saw you did a couple patches to simple malloc. I have not touched it since last week.
I just cleaned it up a little bit. Like I put in little section headers to try to divide out the different sections, and I renamed some of the functions so they were more. I don't know. They made more sense to me. Like it was all just sort of cosmetic work.
Okay. So LD preload, which I haven't used since I was working on Chrome probably, is a way of telling the Linux linker, at least dynamic linker, to insert a library into the linking list, right?
Yes, it is Thursday indeed. Yeah, I think to understand it, you know a little bit about dynamic linking. So when you compile your program, you compile it and you get a bunch of object files and you link those object files together. And then usually that isn't your whole program. You can link a statically compiled program that contains everything. But usually there's a bunch of your program that is not actually in your binary. It's a shared library that comes from somewhere else, like the operating system. And so LD preload is a way of jamming yourself into that queue when you're not supposed to be there. It has many applications, usually all horrible hacks. But I remember using it a bunch when I was doing like various security research, because you can sort of jam your function in the middle of somebody else's binary and like muck around and see what's going on.
I should say the description that you gave, very useful and high level, but it's A, very C biased, and B, is I'm not sure like if somebody came would have enough. Like so, because like if you grow up with JavaScript, right? There's no linker. There's no, I mean, everything's dynamically interpreted, let alone linked. But so in like the C land, in compiled languages, the linker, or sorry, the shell or whatever, the kernel that's forking and execing is looking for a main symbol in an object. What is an executable?
Oh, it depends on the OS, but let's take Linux as the example. Then it's an ELF file. Mm-hmm. So the ELF file basically has a lot of sections in it, and then it has a bunch of strings that says main is over here, its code is here. The foo function, its code is over there.
And so when you are typically making C or other languages that produce object files, your C code is turned, I assume, into assembler. There's several steps in the chain, but in the end, you end up with this binary blob that's a .o file that then can get smushed together to form like an archive, or smushed together to form a library, or smushed together to form a executable. And that smushing is the linking.
Yeah, and what's really important about the linking step is it destroys information, and that allows the linker to do a bunch of optimizations. So when you have compile all your separate O files, all of your code is there, like every function you wrote. Mm-hmm. But when you smush it all down, let's say there was a function you never called, the linker can be smart and be like, oh, you never called that function, forget it. Let's not even put it in your binary. And so the information about what that function does is lost. And so when you typically when you link an executable, you say, okay, I'm going to enter here at main, and I don't care about the rest of these symbols. But when you link a library, you have to say, okay, I'm exporting these 4 functions, and the rest of the functions are all internal implementation details that you should feel free to destroy their information if it would make my program better.
Yeah, so those 4 things that you're exporting, you've marked those as external symbols or exported symbols, and those are then roots from which to explore out if you're doing link time optimization, which is a relatively new, I don't know, feels relatively new. I feel like when I started way back in the day, GCC and stuff didn't do link time optimization, or GCC wasn't.
Even back in the day, but very, very simple ones, like dropping entire O files. Like, oh, no one ever referenced any code in this O file. Forget it. Like, we don't need it. Now, of course, it's very sophisticated. They do like inter-function analysis and link time inlining, and you could all kinds of amazing stuff.
But I think what you said was key, of that the .o file creation, the object file creation, is dumb. It's like a dumb translation from C to whatever intermediate formats, whether it's assembler or IR or whatever the like, to then just splatting out a binary representation of the C code that you wrote.
That's right. And the linking is also fairly dumb in that sense too, where like, especially for C, it just uses literally the name of your function. Maybe sometimes it adds an underscore to the front, but that's all there is. Whereas if you're linking C++ code, they mangle your names, because in C++ you could have two different functions with the same name that take different arguments. And so the way they link those is they encode all the types and numbers of your arguments into your name. And so you get this really ugly mangled name as your simple name. And then if you're Go, they add a Unicode dot in your symbol, because they know that no C program known to man has a Unicode dot in the middle of it. And so that's how they get their own linking namespace that will never collide with the C linking namespace. Anyway, there's all kinds of dirty shenanigans get played at this level of the system.
Anyway, so then that's all the linking, and linking is like compile time, or the linking it like on the developer's machine, that is, statically linked programs, where it found all the symbols that your program needed and it hoisted them all into one single executable. But most programs are written and they rely on dynamic linking, which is where instead of hoisting all that code into your executable, they instead write down a list of, I need malloc and I need this and that and whatever as external symbols. And then they also write down in one of the sections, one of the headers of the ELF file, to say, I expect to find, please link in this path to libmalloc.so.
Yeah, like a really good example is this past week there was announced security vulnerability in OpenSSL. It's a very, very common library. And if OpenSSL was statically linked into every program on your computer that used SSL, you would have a really hard time updating your system to get rid of this vulnerability. But if they're all dynamically linked against a single shared library, then all you need to do is make sure that shared library has the fix, and then all the programs magically get the security fix.
And so what we're going to do tonight is we're going to tell the dynamic linker, we're going to set an environment variable that the dynamic linker, which itself is a library, I believe, or
it tends to be either a separate library or sometimes integrated with your libc.
But we're going to set an environment variable that the linker is going to see and say, aha, I'm going to now insert this other library ahead of loading all these other ones.
Yeah, this is like a long sort of theory talk. Should we try to do it in practice?
Yeah, let's go to the code machine. I was trying to imagine.
Yeah, there's a lot of context to like understand like what is this that we're even trying to do here.
Okay, so here's our fancy simple malloc. We actually are not even building it as a .so yet.
Right. So I think that's the first step, is we need to create an SO that exports the correct symbols.
I think if you just do, you don't want G, you want malloc. Let's see, and it's like I don't remember the flags. Do you?
Dash shared? Oh, single dash, because
we're Unix style or whatever.
Who knows? The command line programs, the arguments for your compiler come from nowhere.
Okay, relocation against BSS cannot be used when making a shared compile with fpic. Okay.
So try.
Why does it want? You just need fpic in order to compile. The fpic is position independent code, right?
Yeah.
Okay. Happier now.
So what did it
actually produce?
What did it make? Why don't you say -o like mymalloc.so?
Yeah, I agree. A little odd that you have to name it for independent arguments.
I'll probably libmymalloc would be a good idea. Oh yes, libsimplemalloc.so. Okay, and let's go see what we got. So like I would read elf-a that thing to see what the heck we made.
Read elf-a. Hello.
Yeah, it's gonna have a lot of stuff.
I remember the Mac version of this is O'Toole.
O'Toole, yeah, because Mac uses Mach-O instead of elf.
Instead of elf, yeah. All right, so here's the magic.
Oh, well, welcome back. Welcome back to the show.
It was one of the very first things that I had to work on was updating the file command. So the file command, this was at Apple. File command knows how to read magic numbers.
And what are magic numbers?
Magic numbers are the first n bytes of a program that like have to be unique or at least documented. So you can like file lib. And so then file has it goes and it reads the first few bytes of that file and it's like, I will look up in my dictionary, which you can go find the text file that's the dictionary on your computer. And it's like, aha, this is an elf, blah, 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 whatever. Anyways, that's the great thing about all these like Linux and Unix stuff. You can all understand it. It's all crazy, but you can all understand it.
The information is all there. You just have to keep digging.
Keep reading man pages. Elf64 data. Okay, what are we looking for here?
We're looking for the symbol list.
This is section headers.
Yeah. Keep
Program
going.
headers.
Here we go. No, keep going.
We haven't marked any of our things as export.
Yes, I'm curious whether.
I wouldn't expect to see that.
Oh, here we go. What is this? Oh, okay, undefined. Undefined means we don't have this. We're looking for this to be provided by somebody else. So we want glibc's mmap. We want glibc's printf, and then here function global. This means these are the things that we're exporting. So we're exporting my malloc, my free, dump heap, and init heap.
Okay, those are reasonable. Except we actually want to export malloc.
Yeah. So we need to actually export malloc. I think there are 4 functions we got to do. We got to do malloc, free, realloc, and calloc.
All right, so we could use like pound defines and rename these things, but I think we're just going to call them malloc.
Yep. Okay.
And this header is for the compile phase, not for link phase. It doesn't actually do anything.
Yeah, and we're going to need to make the malloc like self-initializing.
Yes.
But that's going to be pretty easy. Like if we take the pool size.
I see. It's already added my calloc and my realloc. Oh, these are not implemented though.
Yeah, we added them, I think, in the first episode.
But the linker was smart enough to know they don't. They're just declarations, not definitions. All right, you're doing. Whoa.
That was not what I wanted. What have I done?
I don't know. You pasted a YouTube link.
Okay. Well, the sharp eye can go see what jokes we were telling each other before the episode. Okay, so I just added this thing here to malloc that says if the pool is 0, init the heap.
But I got to do gpool size.
Yeah, equals pool size.
Yeah, that was the thing that got pasted over.
Okay. Yep. Okay. So we got malloc, we got free, dump heap. So we need calloc. So calloc, I think, is pretty easy.
Oh, you can try running it, but yeah, it's just gonna crash either at the linker or at runtime. Okay. So this is a clearing alloc. So it's gonna set everything. It's gonna set all of the memory that it gives you back to 0.
Yeah, this is not the most efficient version of this. Like the most efficient version would like realize that data memory it got from like mmap is already zeroed and things of that nature. So this is actually really bad because this will actually cause touch every page.
Yeah, because most of the memory that you get from the system itself is just a promise for memory, and it doesn't actually do anything. It doesn't actually create the memory until you touch it. And so, as you said, this is bad.
That's an optimization for another day.
And realloc, we can just do the same thing, right? We just free BR and we. Oh no, we got to copy it. No,
It's okay. Well, let's just say we'll do something very, very dumb here as well. New PTR is just malloc the size, mem move. Oh, mem copy, new pointer size, free the old pointer, return the new pointer.
Yep. Terribly dumb.
To check whether the node is large enough to fit the new size, and just update the metadata. Data, and then always allocating new data. Yep.
Okay.
So the other thing, by the way, that we don't have that's very normal in mallocs is we have no lock, because malloc and free can be called from any old thread. So I think it's gonna be fine. I think we'll just want to use it with single-threaded programs.
Sure.
Our simple malloc does not handle concurrency yet.
Before we go, I want to, since we've been talking about man pages, let's look it up.
Oh, that's a good idea.
Glib?
We're gonna find out that we spelled it wrong.
In the graphics for the show?
It's described in ld.so, in the man page for ld.so.
There's also man may have this capability now, but back in the day there was a separate program to search through man pages. I don't know if that's still the case.
I use Google to search through man pages. If you type in man space and then the thing you want, Google will figure out, no, you actually wanted the man page for ld.so because it has the thing that you're trying to find the man page of.
Whoa, preload.
Yep. If you search in here, at least the one that I got on Google talks about LD preload.
LD preload. Also, the man is using, I think it's less is the default pager. And if you hit /, you can start searching through it. All things I learned while I worked on.
Yeah, less has like a lot of Vim key bindings.
Oh, that's a Vim key binding. I used Vim briefly and then. All right, preload list. Preload.
I think there's a more relevant one.
What is this for?
I think there's a more relevant description later in this file.
Is this saying that I can pass this argument to who am I passing these arguments to?
I imagine in the interp line. Yeah, you can run the preloader as an executable. Like it's a self it's a self-loading thing. Like it's just you just map it into memory and run it. Like it doesn't require any loading.
Okay then. Yeah. Let me preload. A list of additional user-specified ELF shared objects to be loaded before all others. Okay. Selectively override functions. Oh, okay. So you can just override a few functions, not all of them. Not whole files.
You can jam in individual functions.
So this would not catch then if we failed to override realloc and calloc.
Yeah, I think horrible disasters would occur.
Because you'd be allocating with ours and then reallocating with the system one.
Yeah.
We would all be very sad. Okay. Understands tokens? What? Origin lib platform. I see. This is for you to be able to set things that are like relative to where this program is being run, where it's finding its libraries.
Yeah, like library resolution is a very complicated topic. Like where does it look for libraries, and can you specify entire paths or whatever? So
where I last used this was with lib gmalloc. Well, anyways, you can search for libgmalloc. It's like a guarded malloc. It'll run your program slower, but it will crash if you do anything wrong. Okay, so shall we try?
Yeah, let's try it.
We want LD preload equals lib simple malloc.
Oh, did you rebuild it after we added the extra symbols?
Probably not. Whoa.
Oh, we need to include some header to get memcopy and memset. Probably memory.h. String.h.
Of course.
Of course, because clearly we're working with strings. Okay, see if that works.
I mean, in C land, there are no strings. There are only char stars. All right. Implicitly memset.
Mm-hmm.
Yeah, it did not. That did not do it.
String.h, not strings.h.
Yeah. You deleted. What to do? This.
Sorry.
It's fine.
My editing skills in this episode are not so great.
Okay. Clang. I think it's rebuilt. Okay, so now we want to do LD preload.
Mm-hmm.
We're setting this environment variable. Lib simple malloc,
mm-hmm.
and then ls.
It worked, but did it work?
Well, it's unclear that it actually did anything.
Well, why don't we add a print statement to our malloc, which will then tell us what's going on. Let's add a print statement to init heap so it doesn't spam it a lot.
You don't want 1,000 print statements?
I'm actually going to add a write statement because I don't want to. You got to be really, really careful when you're inside malloc. You don't want to re-enter malloc because if you call a function that then calls malloc, who knows?
So you're going to write to 1, which we believe should be standard out, or is that standard error?
We can give it a better std.
There are no better names in C.
Yeah, there are. File no. All right.
He's a doing it live kind of language. Okay.
All right. So then we just need.
What's the header for this?
I'm sure it's Unistd. Unistd's got everything. Unistd's great.
Okay.
Wait, do we put a new line in? Where'd it go? We totally need a new line.
Why?
And we need the length. 17.
We need a new line where? Oh, I see. In the heap initialized.
17 correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17. Yep. Okay.
I see. Because you have to tell it. So this is the file descriptor you're writing to.
Uh-huh.
This is the buffer you're writing, and this is the length of the buffer.
Correct.
Good times.
It's the knives are made of stones.
Yeah. And we're wearing bear skins. I get it. Okay, it is not using our malloc.
Now I am sad.
No, it's because I missed an E.
Aha. Okay.
All right.
Object
is
is simple.
Like the path?
Try an absolute path. Try putting like $pwd/. Or you could go.
I see. You think that because the shell will expand that.
Yep. Oh, that makes a lot more sense. Heap initialize segmentation fault. Now I believe it is using our malloc. It worked way too well with the first time.
Oh, there was that reminds me of there was some CS shirt that a friend had some years ago that was like a haiku. Anyways, it had like one extra syllable, and then it ended with segmentation fault.
Segmentation fault.
I should actually look it up, but it was great. It was a great shirt. Okay.
GDB.
Yes, to the GDBs. Except we don't want to set that on GDB. So we got a GDB.
Yeah, we don't want to run GDB. Yeah, we don't want to. We don't want to run LDB with our malloc.
Do you know how to set environment variables?
I don't. Should we want to look it up?
Set environment variable LDB. You definitely don't want, to run.
Set space env, name of thing, space value.
And then the other thing is we probably want to actually expand it out. LD preload. Thankfully,
no equal sign, a space.
What?
Yep.
Thankfully, modern debuggers have like history recall. So like when we fail this and we have to come back in, it will have the history.
When we fail, Eric, we never fail. We are perfect.
There was that one time.
One time in Bandcamp.
What'd you say?
Go ahead.
There was that one time in Bandcamp where we wrote a Lexer that was correct on the first time we ran it.
Oh, I thought you were going to tell my favorite joke is I made a mistake once in 1970. Oh. I thought I had made a mistake, but I hadn't.
I was not aware of that joke. Invalid command setting. Oh, what?
What? This is totally right off the thing. Oh no! Oh, sorry. You just say env. Env. Sorry, I was reading. This is how you do it in GDB.
Oh yeah, I did. Yeah.
Here they provide the LODB translation, which is just env space and then the equal variant, because of course.
Okay. Right. We did it.
We did it, team.
All right. Run ls.
Okay. Target create. What?
Well, it might not know. Like ls, it has to resolve to it. Like we have to find out where the heck is L. It's probably like run bin ls.
Okay, when you start LODB, you're supposed to pass the binary on the command line.
Oh.
I believe is. Yep.
Okay, so there it created that target. Now, thankfully, we have history to go back, and now we can just run.
Now you can just run. Segmentation fault. Excellent. Okay. Can you do a backtrace? Do we have source?
We don't have source.
Okay.
I mean, we could get to source, but we do not have source. I did not think about this.
Should we look at the assembly? Do you want to just run?
It's showing us the assembly.
I want to see like what happened just before this. Could you type list?
Oh, what did you say?
What list? I don't know.
There's a way to like go back. Like. That's not have anything. I want to disassemble. Yeah.
Yeah, it's possible our problem is alignment because we're really fast and loose with alignment.
Okay.
Like I'm not sure what the rules are for alignment. So let's see what the internet thinks. What is the alignment of malloc? By default, alignment is 8 bytes or 16 bytes. Okay. Malloc on macOS always returns memory that is 16-byte aligned.
Do we have to tell mmap to be aligned, or
no? Mmap will always be aligned, but when we split up the nodes, we split them up in very fine-grained ways. So I think we may want to only deal with 16-byte alignments.
Okay, so all right. So like right here.
Right. So this size, I think we need to basically round up to be 16-byte aligned.
Or round down. Oh, I see. Round up.
Yeah, I think when we're doing this calculation to say, do we want to split the node, we need to figure out whether we need to take the alignment into consideration here.
Well, why don't we just do this? Like right here at this, we just always round up. Is that reasonable?
That's not quite the same, right? The alignment is about like where the starting address is. Mm-hmm. You can still allocate like 1 byte long. You just have to have the right starting address.
Why don't we write the align function?
Yep, that's going to be an important function.
And then
Well, we want to align sizes, I think.
Okay. Fine. You sure?
Yeah. Then we want to. Oops. Copilot had a suggestion.
Okay.
I was very interested in. Okay, that looks like a reasonable align function.
Okay. And then
This is
do
align
we
A.
align both this?
I think we always want it to be that the header is always on an 8-byte alignment, and so I think here the new node, we want to make sure that this new node pointer is always 8-byte aligned. So this is like size t align size is align native size. And if the current size allows us to create a minimum free node.
Why don't we just change size to be aligned size here? What's wrong? Like, why do we ever want, this feels like a foot gun.
Okay.
Well,
So,
but my concern is that we might check align size now, but then use size later and then be sad at ourselves. Or would we?
well, we use size for, there's two different purposes for size, right? One is making sure that the size is going to fit in this node. And the other is, do we have enough room to create a new node?
Mm-hmm.
And those are different questions.
Okay. Do we need to force ourselves to use the correct ones? Do we need to rename this variable? Like to requested size, just to force ourselves to change?
Okay, so let's do that. That's a good idea. So requested size.
That does force us to analyze each call site and make sure we're using the correct one.
Yep. So if the current size is greater than or equal to the requested size, and we have if the requested size is 0, then forget it, you get back null.
Yep.
The current size is greater than or equal to the requested size. Great, we're going to use this node. Now we need to compute, now this thing is we need to figure out.
Is that true? Because this could end up being, we think we're going to use it, but it could end up being too small if the requested size needs to round up.
Well, but let's say you request 1 byte, right?
Mm-hmm.
As long as the node has space for 1 byte, everything is fine.
Okay.
You get an 8-byte aligned pointer that has 1 byte of storage available in it. I think that should be okay.
I'm willing to trust you. I don't have. So this obviously can change. But what about all these? Split the node.
Well, I think we should change this calculation. So we want to find a pointer for the we're currently doing this based on size, but I think we want to do it based on this new node pointer.
Okay.
So let's try to compute where the new node pointer would be. Like potential, so the new node, if we were to create one, would be at the current plus this plus line 8 of requested size.
Okay.
And now the question is, plus size of body.
Well, if body is less than, oh, never mind. That's for a free node.
Right. So we still haven't dealt with this. This is fine. So the first condition is is the new node, we want to know, is the new node contained in the old node? Right. So that's basically says current
this is the would the new node start within the. Yeah.
And then the second question, like, is the new node big enough to bother creating? Which is where we're going to use the minimum free node size.
So we'll move that down to that consideration. Yep.
Yep. Right, so this is sort of the offset. This is the like const size t offset for new node is this, right? Okay. And then we want to know, like, to answer this question, would the new node be contained in the current node? We can compare, we can say if offset for a new node.
Isn't this going to get us just into trouble? Like, I see the struct node, the node is the header.
We have a function for this that we could use here, which is get pointer. This is just get pointer.
Okay. Of current plus requested size. Oh, I see.
Yeah, so basically, like the pointer plus the requested size is going to be given to the customer. Then we're going to align that to an 8-byte boundary to get the next thing.
Well, we're moving from node point. We're getting the pointer,
mm-hmm.
and we're going from pointer land to offset land. That feels bad.
Right.
Because we had talked about before, like you should only ever go from pointer node to offset mode by subtracting 2 pointers, right?
Mm-hmm. Right. This line is incorrect. So what do you think we should write here instead?
I guess I'm still trying to wrap my head around what we're doing. Maybe we can write the pseudocode here.
Right. Let's draw a picture. Okay? I think a picture would be helpful. So we have, what's going on? We've got the node header, node body free space. Thank you. Thank you, Copilot.
Copilot can draw diagrams too.
And then afterwards, we're going to have the node. This is going to be, this diagram is bad. So
we can draw bad diagrams.
Right now we have node and free space, right? We starting with that. And then the question is, do we want to create node? This is going to be the client region.
Mm-hmm.
Okay. Then there's going to be free space for alignment, which is the part that we're missing. And then there's going to be another node and a free space. Or we just create node, client region, and free space. The question is there enough extra space here to be worth creating this thing?
Okay. All right, so question, is there, if we allocated the client's request from the current node's free space, would there be enough left over to preserve, to create a new node?
Right. So I think we can answer that question by adding up all these spaces. So we can say, so the client region plus the free space for new line is a line 8 of requested size. So size t, align size is align 8 of requested size is sum of the client region and the free space for alignment. Okay, and we know the node size, so we can say if the align size plus the size of node plus okay, so then the minimum node size here, this is the sum of node and free space. Okay. And the sum of node and the least free space we're willing to create, we're interested in. Okay. So then we could take the align size plus the minimum free node size and compare that to the size. So if the current size is greater than that, then now it's worth creating.
Okay.
Do you buy that?
I think so. I think the thing that I'm worried about here is when things need to be aligned versus not. And do we align offsets or do we align pointers?
So the thing that we need to be aligned is the client region. So the goal, overall goal, oops. Every client region is 8 byte aligned. Strategy.
An 8-byte align means that it starts at an 8-byte offset?
Yeah, i.e. starts at an 8-byte offset.
So why does that matter about the size then? All that matters is that the final pointer that we give them.
Right. So our strategy for achieving this goal is always align nodes at 8-byte boundaries.
But does that mean we align? That means we align the client region of the node at 8-byte boundaries, not the node itself.
Well, the node itself is a multiple, like static assert size of node equals align 8 of size of node. Node must be 8-byte, must be a multiple.
Okay.
Of 8 bytes.
Also, I can't tell how much of this is just that, because I remember reading C code, you often see these just, pages and pages of comments.
Well, because you end up doing all these like dirty tricks, and like in the end, you're just gonna like add a bunch of numbers and mash a bunch of pointers, and like no one has any clue why you did any of that. And so like you like work through your reasoning process and like draw diagrams of this is how memory looks like, and this is how we've done all this stuff, and therefore when we match these numbers together, something sensible happens.
But how much of this is C, and how much of this is that we're doing something complicated, or maybe it's just a mix? Maybe it's just both. Also,
I think when you work in another language, you build up abstractions, and so the code ends up reading more like what this text is reading. But here we're like ripped apart all the abstractions. We're just staring at raw memory, and we're like, we want these like numerical things to work out for us, please.
Yeah. Sorry, I gotta plug in my other computer here.
No worries.
The stream is frozen for it, which I think is just it ran out of power. I don't know. We'll see. We'll see if it comes back to life.
It's working for me. I hope it's working for the audience too.
All right, good. Okay, I like that static assert.
Okay. So, all right. So new node. Oops. Okay. New node size is minus align size. Okay. Current size equals align size. Okay. I have a lot of red squiggles. I don't know. Do you have red squiggles?
Yeah, I do. I haven't traced down why yet. Here, let's see what it says. Node is undefined.
Okay, I'm gonna move the static assert up to here. Great. Node is undefined.
Mm-hmm.
Where's
struct node?
Struct node is undefined.
Yeah, probably because we're missing a.
So something horrible has gone wrong.
Yeah, the parser got upset.
Okay.
My spidey sense would tell me that we're missing a curly brace.
Yeah,
that's the kind of thing that does that. So I'm looking back to see. Why do you want to move the static assert there? Doesn't it not care?
Oh, okay. I don't know.
I don't know. I don't think it's going to run the static assert every time malloc is called.
No, for sure. It's a compile time thing. Oh, size of node. This is where we have this struct node. Size of struct node.
Okay. Because in C, you have to tell it when the thing you're asking about is a struct.
We can make type defs, but that's
what? Fine. What test?
We can make type defs if we wanted to.
Oh, okay. Yes. All right. We're still the pandas are still sad.
I think it's confused. Can you just actually try to run the compiler and see what it says?
Uninterval constant.
Yeah. Okay.
You performing surgery?
I can't call a line 8 in the middle of this static assert.
Line 8 would have to be a macro.
Does C have const expr? C++ has const expr. Const expr in C. Not a thing. Not a thing. Yeah, go ahead. You're gonna make a macro? Go for it.
Is this?
That's fine. We'll just make this 8.
Okay. It's terrible, and
yeah,
angles have lost their wings and all sorts of other things. But
okay, now what does the compiler say?
Whoa. Okay, hold on. Where'd we go? This one.
Okay.
Oh, lower precedence. Oh, this is so okay. This is because remember macros just do textual replacement.
Oh, do we need more parentheses? Oh, we totally need more parentheses.
Yeah, you need more parentheses because otherwise it's just going to splat that in the middle of who knows what, and get sad.
I can make it n. Just for sanity's sake. Okay.
Right. We're still sad. Warning. Ampersand.
You gotta wrap the whole thing in more parentheses. Every time you use a macro, you need like infinity parentheses. Okay, try it again. Great.
Okay.
Should we try ls and see if it dies?
Well, hold on. So we think, despite our analysis server or whatever, our lack of analysis server having crashed, we think it works.
I mean, it compiled. It must work, right?
Your all code analysis problem. Sure. What did that do? I don't know. Whatever. It'll eventually wake up again. All right. I gotta clang it. Oh, I just did.
I mean, who knows if this was the bug, right?
So I think we would have to. I think we jumped too far.
Correct.
We jumped all the way to ls, or we need to have something that had source.
Maybe we should try to write a hello world program and try using our malloc for that, and see if that works.
Okay, we're still gonna end up like, sure.
We're gonna not having symbols for libc, which is gonna be a problem. But okay, but let's go there. Hello world. Let's see.
You're doing it?
Sure. Int main.
I haven't shown up on mine yet. Wonder why it hasn't shown up for me.
Maybe I'm not actually allowed to do it. Why don't you do it?
Okay. Int main void. We want F. We're gonna end up just like crashing in printf, right? Maybe not. And we want, what is this? Include. That's not right. What is what's the include for printf?
stdio. I made the printf a little more complicated, so it has a format string, but same idea.
Okay. And so now we can just link in our.
I think it's more fun to do with LD preload, but yeah.
Okay. Clang. Hello world. Okay. A.out.
Oh. So it was our malloc was powerful enough to run Hello World.
It was. I guess another thing we could do in terms of diagnosing, well, like we could start with things where, why don't we add a printf or a write to malloc itself?
Okay. Like a logging kind of system.
Like we just have a logging malloc, right?
Mm-hmm.
And it'd be nice to print the size, but I don't know that that's feasible.
Right. So now you're getting to like, how do I log without re-entering malloc?
That's okay. We can also just print.
Here's how you do it. You do log.
You have to have a buffer. Yeah.
Yeah. Mm-hmm. It's like 1,000.
And then you do sn printf into the buffer.
Yep. We're totally gonna do it. SN printf buffer size of buffer malloc z. Yep. Nailed it.
Copilot has seen this show before. Yep.
Okay. This and then Sterlen.
Yep. Sterlen buffer. Yep. Yep. Routine.
I'm gonna make a static malloc log. My log. Message size t value. Okay.
Whoa.
Here message.
Look at you go.
I may have done this a lot. Like low level logging turns out to be super useful when you're implementing stuff like malloc.
Okay. So sure. Why don't we just start with malloc?
Okay. Well, we do free too.
Well, we're already presumably we're going to have lots of. Well, I just want to see how many mallocs we make. 0. Let me make sure I actually claim it.
I'm not sure you recompile it. Yeah. No, clearly not. What did I do wrong? Oh, it's MSG. Okay.
I don't know why our analysis errors have gone out to lunch, but they have. Whoa.
Bajillion mallocs of size 100.
Wonder why.
Fascinating. Try running our Hello World program. I'm curious what kind of mallocs that does. So one malloc of size 1024. So it is doing a malloc. So it's slightly non-trivial.
That's interesting, though. So, okay, let's log freeze too. See if we're like I wonder what those are. Are those like directory entries or something? And it's just like crawling the.
It could be. That's very possible. Should we try cat? Maybe cat is a simpler program than ls. Yep, I just passed the pointer. You don't have a size there, but you press 0 or whatever.
Well, we actually do get the size, don't we?
Yeah, we do. Where is that?
But it's not the requested size. It's the allocated size. Okay. So you won't be able to pair them in your head.
So interesting.
Okay. Let's see how they inflate. Let's see if we. Okay, so there we never dealloc. Oh, what is it? It's ls. Maybe I didn't recompile it, but I don't see it. I don't see any freeze.
Okay. Can we try something like cat?
Yeah. Or echo.
Or echo. Yeah, echo's a good one. Because that just never calls malloc. That's fine.
Interesting. I wonder if it's libc that's doing the like a bajillion, like when you call cutter, current directory or whatever, it loads up the file system at a bajillion 100 byte mallocs. Okay. I mean, this is an easy malloc pattern to reproduce. We're kind of running to the end of time, but like.
Yeah, I think if I was really going to do this, I would either get more intimate with the assembly to try to figure out what was going on, or I would try to get symbols for these utilities. I don't know where you got this distribution of Linux from, but often because Linux is open source, you can get the symbols.
Oh, in fact, I suspect. Well, this is just Ubuntu, whatever Ubuntu is on my. But I think you're right. I suspect I could do ADB, not ADB.
Apt-get install.
Apt-get install, libc symbols or something, and it would probably show up.
It would, like, with the symbols, it'd be much easier because it'd be like, oh, this is what's going on. Like,
yeah. I agree. Well, I have no idea if that was fun to watch, but it was fun to me to play around in stuff I haven't touched in a long time.
We did get it to work for some very simple programs. It just like once you got into the complexity of ls, it's something fell apart.
Well, my guess would be we're probably not that far. We have probably a big bug, and then we will quickly get to performance issues, where you find that our malloc is way slower.
Super duper slow, and also very fragmenty, and also doesn't return any memory back to the OS when you call free. But for command line programs, it's not so bad because they
touches every page that you ever
Yeah, okay. So it turns out writing a real malloc, there's a lot of work that goes into it, and I actually have a lot of respect for people who do this because you're bashing around at this like low level system and like really inside everyone's inner loops. Oh, great! I'm glad you enjoyed it.
There also just are so many mallocs that have been written because the contract has existed for forever. Lots of memory allocators out there.
Oh, Heshvin enjoyed it. Wonderful, Heshvin. Yes, we should check whether they're calling the other somewhat dodgy functions that we created.
I will commit and leave some of this to the exercise of the reader. I think I will be out next week, so I don't know if we'll have a show next week. And otherwise, we'll see folks in 2 weeks.
Yeah, well, see you either in 1 or 2 weeks.
Have a good night.